Alright, welcome back. Now that we've effectively imported our model and frozen the relevant parameters, we can now take advantage of transfer learning. Using this pre-trained model, we will be able to get very effective style transfer results. So now let's move forward and import the images that we want to apply style transfer to. We are going to have a content image and a style image. The target image is going to be a combination of the content from the content image and the style from the style image. This process begins by defining a load image function that will load our images from a specified file path. So our function is going to take in an image path as an argument, followed by a max size variable. The image path argument is self-explanatory, while the max size variable is meant to control the size of the images used in the process. Larger images take much longer to process, so we are going to put a cap on maximum image size to speed up the style transfer process. Let's set this max size equal to 400 pixels to limit the horizontal and vertical dimensions of the image to be 400. And finally, the last argument is going to be a shape argument to control the shape of the image that is loaded. The role of this argument will become more clear as we continue coding, and I will revisit it in more depth. For now, we are going to simply set it equal to none. And now going inside of our function, we define an image variable to store our loaded image into. And now using the image module from earlier, from the pillow library, we can use the .open function to specify the image path. And concluding this line with convert RGB, we set the color space of the imported image that we will grab from the image path to be a standard RGB image. And now so far, this simple function allows us to import our images from a file path, which is a relatively simple task. The rest of the function is going to allow us to apply the appropriate transformations to this image to make it compatible with PyTorch and with our VGG19 model. Firstly, let's check some conditions to ensure that our image size does not exceed the maximum allocated size that we set earlier. We can use an if statement. If, to check if the dimensions of our image are larger than the maximum value we specified using image.size. Using this, we return the size of our image and we will wrap it with the max command. So using the following, we obtain the highest dimension value of our image, whether it is horizontal or vertical. Now, if this value is larger than max size, and the max size value we defined earlier, we are going to set a size variable equal to our max size. However, if our image dimensions are already smaller than our max size variable else, then we set our size variable equal to the max value returned from our image.size. This essentially leaves the size of our image unchanged, as it is already smaller than our threshold value. Alright, and now what we can do is make a call to the transforms module that we imported earlier from Torch Vision to apply the appropriate transforms to our image, and we also attach the .compose function to chain together all the transformations that we are going to apply. Let's begin this transformation call by initially resizing the image using transforms.resize. We can resize our image to be equal to the size variable we determined earlier. This will make the size of the smaller edge of our image equal to the value of the size variable. As our size variable can only have a maximum value of 400, it means that the maximum size of the smallest edge of our image will always just be 400, while the larger edge of our image will still be larger than 400 pixels. Setting this 400 pixel limit on the small edge of the image still helps to improve processing power and decreases the overall size of the image. This is because the resize command maintains the aspect ratio, the relative size of the horizontal and vertical edges of the image, meaning that when the smaller edge is scaled down to 400, the larger edge of the image is scaled down appropriately as well. Next, we will use the appropriate transforms.to tensor call to convert our image into a tensor. Concluding this transform call, we will use transforms.normalize to normalize our image as we've done in the past. The normalization schema that we will use is one that we've used before. We are simply going to apply a sample, mean, and standard deviation of 0.5, 0.5, and 0.5, 0.5, 0.5, and 0.5. Nothing new. Let us not forget our commas. And these are all the transforms that we are going to need to apply to our image in order to make it compatible with our model and with PyTorch. We can now store the value of transforms.compose into another variable that we will refer to when we need to apply these transforms. We can call this variable in transform. And that is all. Now that we're almost done with the cell, we can call in transform with our image as an argument to apply the transformations that we just specified, and attaching the familiar unsqueeze0 function to add the extra layer of dimensionality to our image, storing this in a new variable image, and finally we are ready to conclude this function by returning our image variable. Alright, now on a new cell we can run the function we have just written to import the two images that we are going to be using. Now before we can write any code in the cell, we are going to need to upload these images into the Google Colab notebook. The two images I am going to be using can be found in the resources folder prior to this tutorial. It was in the article right before this tutorial. So feel free to follow along with the same images as me, or if you feel confident, you can feel free to experiment with your own two images. And now uploading an image is done by navigating to the upper left corner of your screen and clicking this small arrow on the side. You must now navigate to the Files header, and here you will be able to see the Upload button, which you can simply click on to import your files. I have personally stored these files inside of a folder Images inside of my desktop, so I will upload them from here. For now, the Mona Lisa image you do not need. I will just upload City and Starry Night. Now, an important note about uploading files to Google Colab is that any time that you reset the runtime, these images will be lost. So you will have to re-upload them in order to use them again if you were to reset the runtime. And now the content image that I will be using is of a few high-rise buildings in a city at nighttime. And appropriately, the image is simply called city.jpg. While the style we will be applying to this image, we will be using the famous Starry Night painting by Vincent van Gogh. The colors and style textures found in the image will be interesting to transfer over. And now this image file is simply called starrynight.jpg. Alright, and now back to our project. Closing the sidebar, we can now implement our load image function, calling load image with our specified path for our first image, which is going to be city.jpg. We will be able to import our image, but we also need to remember to attach the .toDevice command to allow for the use of GPU when possible. We will now store the return value of this function call into a variable called content, as it will store our content image. And now copying this same line, we can replace the image path name to load our style image, Starry Night. Let us simply make sure we got the names correct onto our files, city.jpg and starrynight.jpg. We seem to be good. And we can also change the name of the image storing variable from content to style. Alright, we have effectively loaded our images into our notebook. They have also been resized, normalized, and converted into a tensor inside the load image function. Alright, now simply visualizing our data will ensure that the import was done successfully. However, before we can import our images, we need to convert them from tensors into NumPy images, ultimately to ensure compatibility with the pyplot subpackage. We've done this before with the familiar image convert helper function that we have previously used. I am simply going to copy and paste this function into our notebook from a previous notebook as we have already covered the logistics behind this helper function. So what you're going to do is feel free to go to my GitHub page, github.com/rslim087. And we're going to copy it from one of the MNIST codes, as that is where we first used it. We go to convnet, that should work just fine. Going over to def image convert, we will copy this right onto our notebook. Copying and pasting the function, alright. Essentially simply taking our tensor and applies all the appropriate methods to convert our tensor into the NumPy image. The details behind each step are explained earlier in the course. Feel free to check that out if this function is still unfamiliar to you. And now on a new cell, we can use our helper function to plot our images side by side using the familiar plt.subplots. We're going to make a grid arrangement with a single row and 2 columns for our 2 images. We'll define a fig size is equal to 20 by 10. And now returning the subplots call into the appropriate fig variable, along with the 2 axes, axes 1 and axes 2. And what we'll do is actually plot the content image on the first axis. And we do this using ax1.imshow. And this is where we'll make use of the imconvert function. Imconvert to convert our content tensor into a compatible NumPy array. Alright, and we will also access axes 1 and set the axes value to off to view the image more clearly. And copying these 2 lines, we change axes 1 to axes 2 in both lines and replace content with style to plot our style image in the second axis. Running this cell, we get an error. Alright guys, so I realized the error from before. The upload should have actually taken seconds. The reason why it took so long is because I was using the Safari browser rather than Google Chrome. So to ensure that your upload works, make sure you're on the appropriate browser. And if that wasn't a problem for you, then I guess feel free to ignore what I just said. Aside from that, I'm just going to rerun all of my cells and I will see you in a bit. And running this cell, we do get an error, the axes not matching the arrays themselves. So what we're going to do is the images that I gave you, we're going to remove single dimensional entries from the shape of the image, from the shape of the array, by adding an intermediary step, image is equal to image.squeeze. Removing the single dimensional entries, trying this again. Alright, this was simply to ensure compatibility in order to plot our images. Now having run the cell, we can view our images side by side. Looks like they were both imported correctly. So throughout the style transfer process, we are going to maintain the content, such as the buildings and object positions of the left image, while applying the texture, color, and painting strokes of the style image on the right. This should be an interesting result. Before moving forward into the process, we are going to make a small adjustment to our load image function to allow for a more effective style transfer. Style transfer is more effective when the size and dimensions of the content image are the same as the size and dimensions of the style image. This also makes the process of style transfer easier when both images share the same shape. While our 2 images here look about the same in terms of size and dimensions, we can have situations where this is not the case. As an example, let's replace our content image with a more vertical image that we will first upload. We're going to use the Mona Lisa image that I included in the resources article earlier. So by going on to Files, Upload, I will upload the Mona Lisa image, placing in the appropriate name, Mona Lisa. Executing this cell, we can see the differences in image size and dimension. So let's make a small adjustment to our code to ensure that the style image always takes on the shape of our content image. So scrolling back to our load image function, We are going to make use of the third argument, namely the shape argument that was not well explained earlier. We have set this input to none by default. However, if this argument is given in the function call, we are going to make use of it. So let's go into our function and add an if statement under our previous else statements. And now this if statement is going to execute if the shape argument is not equal to none. If this is the case, then we are simply going to set our size variable equal to the shape that we have inputted. Size is equal to shape, like so. And now executing this new cell, we are going to make use of this shape argument in the function call using the style image, as we want the shape of the style image to be the same as the shape of the content image. So we are going to set the shape equal to content.shape. Easy enough. As we only require the image dimensions, we will only access the third and fourth index of the image, from index -2 and beyond. Recall in Python, the negative index is used in Python to index starting from the last element. So -2 would refer to the second last index, and so on. Alright, and now when this line is executed, the shape of the content image will be stored in the size variable. The transform call will then make the dimensions of the style image equal to the dimensions of the content image. Alright, let's execute all of the following cells, runtime, run after, and replot our images to see the difference. And there we have it. Now both of our images have the same dimensions. Let's set our content image back to city.jpg, as that is the content image we want to use. This was only for demonstration purposes. And running our cell ensures that our images were loaded properly. And now our style image will always take on the shape of our content image. Alright, and having effectively loaded in our images into our notebook, in the next video we can get started on implementing style transfer.